Hello, geometry students. Mr. Zacek back and better than ever with you here. We're in Unit 12, Lesson 3, and we're going to be taking a look at volume and surface area of pyramids and cones. And we're just going to see a lot of similarity related to prisms and cylinders. So a pyramid is a polyhedron with one base, which can be any polygon. The lateral faces are triangles that meet at a common vertex called the apex. So the apex is the top point here. Big thing that we have in triangular pyramids is we have two types of height. We have what we refer to as the height, which is this perpendicular distance that you see in this figure on the right here. And then we have another thing called the slant height, and the slant height is the distance along the face of it out here. So we may be using some Pythagorean theorem stuff to find the dimensions, where the sum of the squares of the legs equals the hypotenuse squared. So just like we have right cylinders and oblique ones, and we have the same thing here with pyramids. A right pyramid, the center is down here on the base, and in an oblique one, it's just sort of off center. The height doesn't come down to the center. We're going to be dealing with right pyramids primarily. And so a regular pyramid has a regular polygon as its base. Remember, when we see the word regular, we're thinking like equilateral, equiangular. That's what it means for it to be regular. And so all of these, in this case, in a regular pyramid, all of the triangles that you have here are isosceles triangles, and all of them are congruent. So in a pyramid, there's one base, which is a polygon. The lateral faces are always triangles. Pyramids are named by the shape of their base. All cross sections parallel to the base are similar to the base, and a regular pyramid has a regular polygon. Lateral edges are all congruent, and the faces are all congruent isosceles triangles. Okay, so the pyramid is 1/3 the area of the base times the height. That's the volume for it. And again, remember, this big idea is that B, the capital B, stands for the area of the base. You'll see this on your formula sheet. So we have to figure out what's the shape of the base in order to do this. And we can justify this. Basically, here's what happens. If you take this pyramid and you take a rectangular prism with the same height, it would take 3 of these pyramids to fill up the full rectangular prism, or the square pyramid there. So that's the justification for why it's 1/3. Surface area, just when we think about the surface area, it's going to be important for us to find the slant height will be the height of this triangle here if we have a question where we need to find it. So remember, again, with slant height, it's different from the other height of the pyramid, and we have right triangle stuff going on there. Okay, so cone, similar to a cone. A cone is similar to a cylinder, and so we have a slant height, we have a height, and again, this is a right triangle. We may have to use the Pythagorean theorem as a part of this. The lateral area is this kind of funky shape that you see over here, like this, and then obviously the base is a circle. So with cones, we can have right cones, we can have oblique cones, and we see the difference between those there. So all cross sections similar to the parallel to the base are similar to the base. And just like for a pyramid, it was 1/3 area of the base times height. Here it's 1/3 area of the base times the height. Again, the base is a circle, which is where we get the pi r squared from. And the reasoning is the same. If you took a cylinder and you took a cone that were the same height with the same circle base, it would take 3 cones to fill up one of those cylinders. All right, and then so for the surface area of the cone, the lateral area has a special formula here. S pi r gives us the lateral area for that. We're going to focus more on volume. Okay, so find the volume. Leave your answers in terms of pi when possible. So volume is going to be 1/3 area of the base times the height. Again, the area of our base is pi r squared times h. So our volume is 1/3 pi times 9 squared times 18. When we leave it in terms of pi, what that means is we're going to put this in the calculator in this way. So we'll use our fraction template, put in our 1/3 times 9 squared times 18. So it's 486 pi. So the volume is 486 pi cubic miles. That's a massively large cone. Here, pyramid, we have a rectangular pyramid. So the volume is 1/3 the area of the base times the height. When you have a rectangle, the area of a rectangle is length times width times height. So this volume would be 1/3 9 times 8 times 9. Okay, so 1/3 times 9 times 8 times 9 is 216. So the volume here would be 216 kilometers cubed. Again, that's a massively large pyramid. All right, let's try this one. The Great Pyramid of Giza was constructed as a regular, remember when you see that word regular, that means equilateral, pyramid with a square base. It was built with an approximate volume of 2,592,276 cubic meters and a height of 146.5 meters. What is the length of one side of its base to the nearest meter? Okay, so let's see if we can figure this out. So the base is a square pyramid here. That means that the sides of the square are going to be the same, and then the height was, here's where our height is. So the formula for volume would be 1/3 area of the base times the height. Well, we know the volume, 2,592,276 equals 1/3, and here the area of the base is a square, so that would be x squared, or x times x, and then the height would be 146.5. Okay, so here's what we're going to do. Algebraically, to get rid of this fraction, let's multiply that by 3 first, both sides by 3, and then we'll divide by 146.5. All right, so 2,592,276, 2,592,276 times 3. Looks like I left. Yeah, 7 million. Okay, so 7,776,828. We're going to divide that by 146.5. So divided by 146.5. And then we would need to take the square root of that. So square root. And if you hit Control and then that negative button, that's your previous answer. So it would be 230.4. Okay, so x would equal 230.4. So you can write all that stuff out, but so to the nearest meter would be 230 meters. So that's an example where we're given the volume and we had to find a different length with it. Okay, so a pyramid has a square base with a side length of 40. Okay, again, square, keyword here, so that means we know these are all going to be 40. and a slant height of 25. What is the volume? So in this case, what we need to understand here is when our height comes down, that this length would be 20. So our height is a part of this right triangle, and so h squared plus 20 squared equals 25 squared. So this would be h squared plus 400 equals 625. When we subtract 400, we get 225, and when we take the square root of that, our height would be 15. So here's our height of 15. So now the volume of the pyramid equals 1/3 the area of the base times the height. So that's going to be 1/3 40 times 40 times 15. So let's go ahead and multiply that out. 1/3 times 40 times 40 times 15 is 8,000. So the volume here of this pyramid would be 8,000 cubic feet. Significantly smaller than the Pyramid of Giza. All right, candle maker. So a candle maker uses a mold to make candles like the one shown below. The height of the candle is 13 centimeters, and the circumference of the candle at its widest measure is that number there. So we've got a height of 13 centimeters, and using modeling to approximate how much wax to the nearest cubic centimeter is needed to make this candle. So essentially, when it says to the nearest cubic centimeter, this is a volume question. All right. So now we have a circular base for this, and we know that the circumference, which is d pi, so we've got 31.416 equals d pi. Well, if we wanted to know the diameter, we would divide that by pi. So take 31.416, and we divide that by pi, and we get 10. Okay, that works out nicely. So the diameter is 10, therefore the radius would be 5. So the volume of the cone is 1/3 the area of the base times the height. While in a cone, the base is a circle, so this is pi r squared h. So our volume is going to be 1/3 pi times 5 squared times 13. Okay, and so to the nearest cubic centimeter, we're not really worried about leaving this in terms of pi. So we have 1/3, and then the order doesn't really matter how we put this in. If we want to do 5 squared times 13, 340 cubic centimeters of wax. So the volume would be 340 cubic centimeters of wax to the nearest cubic centimeter. All right, so volume is how much we would need in that case. So the office of Dr. Barnett has a water cooler for the patients. The cooler is cylindrical with a 16-inch diameter and a 24-inch height. So we have a cylinder here, big water cooler. Okay, this is the cooler. 24 inches high, 16-inch diameter. Paper cups are provided that are cone-shaped with 4 inches high. Okay, so we got a height of 4 inches and 5 inches in diameter. Approximately how many servings of water can one full cooler provide if on average people fill their cups 80% full? All right, we got a bunch of stuff going on. Start off, we got a diameter of 16, that means we're going to have a radius of 8. We got a diameter of 5, that means we're going to have a radius of 2.5. First thing we're going to do is we're going to find the volume of the cooler and the volume of the cup. So the cooler is going to be the area of the base times the height, because that's a cylinder. So this is going to be pi times 8 squared times 24. So the volume of the cooler, so pi 8 squared 24, 8 squared times 24 times pi is 4,825.49. So 4,825.49. Okay, now the volume of a cup, now a cup is a cone. So that's going to be 1/3 pi times 2.5 squared times 4. Okay, let me see if I can remember all of that. So we've got 1/3 times pi times 2.5 squared times 4. And that is our 26.1799. Okay, so 26.1799. Now, that's the volume of the cup, but we're going to take 80% of that. So to take 80%, you can multiply this value, convert the percentage to a decimal, and we can multiply that by 0.8. That'll give us 80%, so 20.944. So 20.944. So that's how much the cup is. All right, so how many servings? So we're going to take this number here. So the servings are going to equal 4,825.49 divided by 20.944. So 825, excuse me, 25.44 divided by 20.944. Whoops. Divided by 20.944. So that would be 230, approximately. So we could get servings would be 230. All right. Good kind of question. So this is the type of question that we could kind of expect to see. If it's very seldom is it a straight volume of one question. They like these sort of combination cylinder cones. And then the other one that we see often asked is related to truncated cones and pyramids. So a truncated cone or pyramid is created by slicing off a part of the cone that contains the vertex. So if we just took this top cone off or this top part of the pyramid off, that would end up with this. So how do we go about that? Well, when finding the dimensions of a truncated cone and pyramid, such as the radius or height in a cone or the length of the base, similar triangles may be used. So do you see what we have going on here? If I'll get my highlighter. All right, this triangle here, the yellow triangle, is similar to the green triangle. All right, and over here the green one, and then we'll do a yellow one out here. Those are similar, and what do we know about similar things? Well, similar things are proportional. So we're going to use those proportions to find either the radius or the height that we need to find. So number one, a water cup in the shape of a cone has a height of 4 inches and a maximum diameter of 3 inches. What is the volume of the water in the cup to the nearest tenth of a cubic inch when the cup is filled to half its height? Okay, so let's draw a picture. So, oh, I still got my yellow. So we got this cone here, right? And the cone is only filled to half. This is a truncated cone. And so a water cup in the shape of a cone has a height of 4 inches. So this height here would be 4. Now, and it has a diameter of 3. So we're trying to figure out what is the volume of this. So we're only filling it up down here. So what is the volume of this here? Well, we know if it's halfway that the height down here would be 2 inches. What we don't know is what is the diameter of this going to be, or what is the radius of this going to be? Well, the radius up here would be 1.5. So I'm just going to draw these two triangles separately. So I got 1.5 with a height of 4. And now I want to know what is this when the height is 2. So we create a proportion. So 4 and 1.5, 4 matches up with 2, and this matches up with x. So we cross product property. Okay, so 4x equals 2.15 is going to be 3, and we're going to divide by 4, and that's 0.75 or 3/4. So that would be our radius down here. So now our volume of this green section is going to be 1/3 pi times 0.75 squared times 2. See, we're only finding the volume of this green cone up here. So we've got, put this in, so 1/3 times pi times 0.75 squared times 2 would be 1.1781. So 1.17 would be 1.2, and it rounds up to it. Okay, so 1.17. All right. So truncated ones are a little tricky. Let's just do one more of these here. We'll do number 3. Okay, this was a part 4 question, I think, for a number of years ago. Water glass can be modeled by a truncated cone, a cone which is cut parallel to its base as shown below. The diameter of the top of the glass is 3 inches. The diameter at the bottom of the glass is 2 inches. So what they're showing you here is this is the glass is part of this cone. So we've got 3 inches, 2 inches, which means we're at 1.5 and 1 for our radius. Okay. The base with a diameter of 2 inches must be parallel to the base of the diameter of 3 inches in order to find the height of the cone. Explain why. Okay, so the diameter is 3 inches and the height of the glass is 5 inches. Okay, so 5 inches. So why is it that they have to be parallel? Is parallel makes the triangles similar by angle, and therefore proportional. Okay. So determine and state the height of the larger cone. So we've got here in this example here, we've got our cone as we come across, and we come down here. We've got this big triangle, and then we've got the triangle down here. And here's what we know. In this one we've got 1.5, in this one we've got 1. Now we know this is 5, so we could do, if we call this x, then we have x and we have x plus 5. Okay, now x is this length from here to here. So this is a tricky question. All right, so determine and state in inches the height of the larger cone. Well, it's proportional. So x plus 5 and 1.5, and then we have x and we have 1. So when we do the cross product property, I get 1.5x equals x plus 5. So if I subtract x from this, I get 0.5x equals 5. And when we divide by 0.5, x equals 10. Okay, so x equals 10 is not the height of the larger cone. The larger cone would be 15. So the height of the larger cone equals 15. So that's this whole thing right here. Determine and state to the nearest tenth of a cubic inch the volume in the glass of water. So now we've got to figure out, so this is our glass of water here. How are we going to figure out the volume of that glass? Well, here's how we could do that. If we knew the volume of the big cone, this whole cone, again, this glass is just sort of taken out from this. So if we knew the volume of the whole large cone and we subtract the volume of the top piece of it, or if we subtract this section of it, that would give us the water in the glass, the volume of the water in the glass. So the volume of the large cone minus the volume of the top cone, I guess, or you could call it the bottom cone. So it's going to be, let's plug in for this, 1/3 pi times 1.5 squared times 15. That's the large cone. Minus 1/3 pi times 1 squared, and then the top piece of this here, this is 10 times 10. Okay, and that would equal the glass of water. So we'll go ahead and we'll do 1/3 pi times, what is it, 1.5 squared times 15 minus 1/3 pi, and then I think it's times 1 squared times 10. 24.8709. Okay, so 24.8709 to the nearest tenth of a meter would be 24.9 cubic inches of water. Tough question, okay? Tricky question, lots of things involved. This brings it all together, okay? So if you have questions on this, feel free to ask. This is a very challenging thing, bringing together a whole bunch of ideas with it. All right, so a little bit of a longer one, but we had some longer problems that we had to work through in this, and you can see how we need to take our time working through these questions. Okay, I'll see you back here soon in our next lesson.